All right, let's dive right into this. You know, when you look at a massive iceberg, we all know the real mass, the sheer scale of the thing, is hidden deep underwater. Well, that is exactly how modern AI works. Welcome to this explainer, where we're going to explore the hidden data pipelines that are actually powering modern AI systems.
When most of us picture modern AI, our minds immediately go straight to the shiny stuff, right? Large language models, crazy complex neural networks, all that advanced math. But here is the reality check. 80 to 90% of real-world AI engineering, it's actually just data and cloud plumbing. No, seriously. Before a model can make a single prediction or match a semantic vector, the data has to be collected, ingested, cleaned, structured, and served efficiently. That shiny AI application, it is literally just the very tip of the iceberg.
So, how exactly do we build that massive underwater foundation? Well, here is our roadmap for today. We're going to start with an AI reality check, map out the data landscape, compare lakes versus warehouses, navigate some tricky engineering trade-offs, and finally, look at how this plays out in real-world AI systems. Section 1, the AI reality check, where data reigns over compute. You see, while earlier eras of computing were mostly bounded by raw processing cycles, just getting enough compute, modern AI is fundamentally bottlenecked by data. We're talking complexity, volume, and sheer velocity.
Moving on to Section 2, mapping the data landscape, or what I like to call the ecosystem of systems. Because to handle that massive volume I just mentioned, we really have to map out the specific technologies that collect and transform this flood of data. If you look at the modern data landscape as a whole, it's kind of like a giant funnel. Raw data at the very top, stuff like IoT sensors or messy web logs, flows down through ingestion and storage layers. From there, it gets pushed through these massive distributed processing engines before finally routing into the highly specialized analytics and machine learning workflows at the bottom. It's this beautiful, massive ecosystem of systems all working in tandem to actually create value. And we can actually break that sprawling architectural flow down into 6 distinct phases, which we call the data-to-insight lifecycle. It kicks off with collection, then moves right into storage, processing, analysis, and visualization. But, and this is a big but, the absolute crucial point here is phase 6, action. The true business value of this entire lifecycle, it's only realized when that final action, like an automated supply chain adjustment, creates a continuous feedback loop that actually improves the model over time. Now, something totally fascinating has happened recently in how we process all this data. As many of you probably know, we've largely moved away from traditional ETL. Why? Well, because modern cloud platforms give us virtually limitless, ridiculously cheap storage and scalable resources. So the industry shifted to ELT. We extract the raw data, load it directly into the cloud as is, and then transform it later using the database's own massive compute power. I mean, it's an absolute game changer for efficiency. Which brings us to Section 3, storage layers, specifically lakes versus warehouses. Let's look at the foundational storage layer where different tech serves completely different architectural purposes. Just as a quick refresher on storage paradigms, think of OLTP, operational databases, like a super fast-paced grocery store cash register. It's handling single transactional records instantly, and it absolutely has to be 100% accurate. You know, like money leaving one bank account and entering another. On the flip side, we have OLAP, or data warehouses. This is more like corporate headquarters analyzing, say, 5 years of global sales trends. It is not looking for a single Tuesday receipt. It's built to aggregate massive metrics across literally millions of rows. But the plot really thickens when we bring AI into the mix. So when do we use a data warehouse versus a data lake? Well, a data warehouse is kind of rigid. It relies on a schema-on-write philosophy, meaning the data has to be perfectly structured before it's even saved. It's fantastic for audited, predictable business reporting. But a data lake? That is all about flexibility. It uses schema-on-read, storing raw, unstructured data, think video files, messy weblogs, in its original native format. And because it preserves that data in its purest form, the data lake is the absolute go-to engine for raw machine learning experimentation. And you know what makes managing these massive lakes and warehouses possible today? It's the defining cloud principle of decoupling compute from storage. Back in the day, legacy databases tried processing hardware and physical disks together on the exact same server. Today, modern cloud architectures completely separate them.
This is huge because it allows organizations to scale their cheap storage capacity up indefinitely, while independently spinning those expensive compute nodes up or down only when they actually need them. We're talking massive overhead savings here. All right, Section 4, Engineering Trade-offs, Navigating System Limits. Because even with all this cloud magic, building these systems presents a classic architect's dilemma. To quote the ultimate engineering mantra here, there are no absolute solutions, only trade-offs. You know, novice engineers often go searching for that one single perfect technology stack, but a seasoned architect knows you constantly have to balance system constraints. Things like performance, scalability, reliability, and of course, financial cost. So the true answer to which database engine is the best? Well, it's always going to be, it depends. Let me show you exactly what I mean. Different access patterns require highly specialized tools now. You can't just slap a standard relational database on everything anymore. If you want to traverse highly interconnected social networks, you're going to need a graph database. Tracking continuous timestamp telemetry from IoT sensors, you absolutely need a time series database. And if you are building an AI chatbot using retrieval augmented generation, or RAG as we call it, you need a vector database specifically designed for those high-dimensional embeddings generated by LLMs. And on top of all those technical trade-offs, architects also have to build around rigid ethical constraints. When you're architecting these pipelines, you have to remember that ethics isn't just an afterthought, it is a hard system constraint. We have to constantly balance that big data urge to just hoard as much information as possible against strict legal requirements. Things like GDPR, the right to be forgotten, and data minimization. Basically, we should only be collecting what is absolutely necessary for the application to function, nothing more. Okay, Section 5, Real-World AI Systems Operating at Massive Scale. Let's actually see how all this theory builds real systems out in the wild. Let's look at retail AI first. How exactly do massive megastores handle weather-driven demand forecasting? Okay, imagine a hurricane is coming. Retail chains create these complex ETL pipelines to join their distributed historical sales logs with external, semi-structured weather APIs. By feeding all of this into machine learning models, they can predict highly localized demand spikes for very specific items. This ensures they dispatch exactly enough emergency supplies, like flashlights and famously strawberry Pop-Tarts, to specific stores days before the storm ever makes landfall. And what about Netflix? I mean, their recommendation engine is basically a masterclass in data pipelines. They don't just rely on those explicit 1 to 5 star ratings you give a movie. No way. Their pipeline ingests massive streams of implicit behavioral data. We're talking about what time of day you watch or exactly when you decide to hit the pause button. They use this incredibly rich, raw data to train complex collaborative filtering models that ultimately rank and personalize that very familiar grid you see on your homepage. But wait, Netflix takes their data even further with predictive content programming. They ingest visual engagement metrics, like literally testing the optimal color combinations on promotional artwork using multi-armed bandit algorithms. And then they combine that with massive audience demand metrics for specific actors and directors. This sophisticated pipeline is so good, it allows them to confidently greenlight multi-million-dollar original shows without ever needing to shoot a traditional TV pilot episode. They are literally using data architecture to completely bypass legacy industry guesswork. It's wild. Which brings us to a final, pretty critical question you really have to ask yourself. Are you building a true AI system, or are you just creating an unmanageable data swamp? As we've seen throughout this explainer, true AI readiness isn't about just slapping a shiny new model on top of a bunch of chaotic files. It requires serious data governance, scalable cloud infrastructure, and a really deep understanding of the pipelines hidden underneath the surface. So take a hard look at your own data landscape today. Are your foundations actually strong enough to support the future of AI?